Afternoon, ladies and gentlemen. Thank you for joining us on this case study of EKG, electrokinetic geosynthetic. Brookhouse. We'll be taking you through this. Let's do a bit of housekeeping. I'm sure you're all familiar with this. Just click that away. I'm sure you're familiar with this. You're all on mute. In terms of a chat box, we'll be able to post your questions and we'll deal with that at the end of the presentation. We look forward to seeing what you think about the presentation and think about the technology that we're going to go through. In terms of an introduction, my name's Dave Capstick, Business Development Manager at Central Alliance. I've been joined on this by my colleague, Matthew, who's a Senior Geotech at Central Alliance. He'll be helping and doing the questions and juggling those around and commenting at the end of the presentation. Okay, so without any further ado, let's move on and see what we're about. So we're going to be talking about a case study at installation on Network Rail's properties. Brookhouse with EKG. This installation was conducted at the end of last year. We've done a preliminary report on this, which has seen a third-party review by Tony G and partners, and that has been fed back to Network Rail, and we are waiting on their feedback in terms of their impression of the project as such. Now we'll go through about certain aspects of the project, but quite obviously as well, a number of you may not be familiar with EKG. So I'll do a broad description within the presentation of the fundamental elements of electrokinetic geosynthetics to help you understand why and how this thing works. So we'll go through an introduction, we'll look at the objectives of the project, the design, implementation and installation, the operation of the pilot site, obviously the results, and then comparing, the results from actuals to design is always an interesting thing to do. Key features and the lessons that we learned from the project, and then just a bit of a summing up in terms of what benefits that we saw come out of the work. The image that you see to the right is our slope climbing rigs that are used to insert the anodes and cathodes that are required for this sort of operation. So just before we jump on to Brookhouse, probably got to emphasize that this isn't a first off and the first time we have done this sort of work. There's an array of installations we've done over the years. You can see on the left-hand side, that's at Highways Agency job at A1 Stocks Green. On the right-hand side, there's the A419 in Swindon. Again, a sort of smaller sort of rig placing in anodes and cathodes on that pretty steep slope. And if you look closely, if you follow my pointer, hopefully you can see it. You can see there and the anodes and cathodes being placed amongst a fair amount of trees. There's other sites we've done in the past as well. The M5 at Junction 9, South Greenford was a 25-metre length of slope material that was causing some issues. That was done in 2009. So quite obviously we've been doing this work for some time, and it continues to grow as an accepted form of dealing with clays and fine-grained soils that are not easy to dewater by conventional methods. So let's have a look at EKG itself as a methodology. So like I say, this is not a silver bullet. It doesn't solve everything. It's particularly good where you've got clays and fine sills, where normal hydraulic dewatering applications don't really cut the mustard. So it's for those difficult fine grains clays, whether they be in natural slopes or embankments. What EKG does is work on a number of levels to deliver a much more compact, stabilized, dewatered area at the end of the project. And it does this by electroosmosis and ground improvement. So compaction due to dewatering. Also as well, at the same time, we're looking for reinforcement around the anodes. You get cementation. And then thirdly, the third element of this is that the cathodes themselves become drains. And you can see from the image on the right-hand side, in this case, it's a vertical installation. So on the left-hand side, you've got a positive anode. On the right-hand side, you've got a negative cathode. And you've got osmotic flow passing from one to the other. So soil moisture will generally throw to the right-hand side into the cathode. It would pond there, and then in this case, because it's vertical, we would pump it out with a small pump. At the same time as that osmotic flow is happening, we've got cementation around the anodes, where metal ions are precipitated out into carbonates and sulfates and other forms to create a cementation around these anodes. And if you look at the bottom, there's a sort of schematic there where you've got cathode horizontal drains in blue and a larger number of anodes in a sort of grey colour, yeah. So here's another schematic view, but this time on how we apply the current, because this is what makes these things happen. And you see an array there, a schematic array, where you've got an AC and a DC unit. We use DC power to deliver the required current, and going across the slope horizontally, we've got a number of cabled anodes, and you can see they're in a sort of yellow, orange and red color. So we've used a different arrangement whereby we can better maximize the treatment across 3 different sets of anodes using different styles of current, so we can be much more efficient in terms of how we deliver the current. The vertical blue system there is the draining cathodes, and you can see in this instance the schematic, it drains into a wee drain at the bottom of the slope. At Brookhouse and at many other sites, we're not allowed to do that. So we collected the water at Brookhouse, put it into IBCs, and in that case we used another RSK company, Remedex, to dispose of that water in an appropriate fashion. One of the key things about EKG is we can work around vegetation. We're not removing topsoil. There's no need. We don't need to take down trees. We can work around them, or we can work around other vegetation, or indeed any other things that are on the slope that don't particularly need moving. As I said, this is a schematic. So the actual Brookhouse installation was 75 meters in length, and the slope height was 6 meters. So let's have a look at Brookhouse itself. So the schematic on the right there is the rail line, and Brookhouse itself is about 10 miles northeast of Brighton. So, and the grey area that's going to go in northeast to southwest is a bridge. This is an area that has caused quite a number of concerns for Network Rail in terms of an asset. A fairly old embankment. It was constructed in 1873, so it's lasted quite a long time, really. It's been causing problems, and Network Rail have been aware of it, and they've had studies and endless studies. They've been monitoring it consistently since 2017, and there was evidence of movement of the slopes and track deformation. In July 2019, Tony G and Partners completed a geotech investigation and a geomorphological survey to identify and confirm where remediation was required. And hence these areas that you can see on the right-hand side, A, B, C, D, E, F, G, came from. What was considered is that Network Rail were keen on looking at a range of solutions. So you can see that slope regrades was used for the A and G areas. A tall wall and counterfoot drain was used for the C area, and counterfoot drains were going to be chosen for B and D. What actually happened is that the area D was thought to be, let's leave it, and we just extended the EKG area to include D. So that was all done by EKG. That would be the 75 meters I spoke of earlier. So out of the options, the 5 options, they only actually chose 4 options. And prior to actually going live and getting involved in the project, a report identified the advantages and disadvantages they thought of each option. So the pros and cons of 5 were noted, as you see on the screen. And the advantages are fairly obvious. And again, given that they didn't know too much about the technology. So the advantages of requires minimum workspace and excavations, well, quite obviously. Very low noise and vibration, comparatively speaking to the other options. Improved drainage measures left on site, that would be the cathode drains, quite obviously, yeah. And improvement of embankment strength and stiffness, both through dewatering and also through the legacy of leaving soil nails around the anodes, and also grouting some of the non-draining cathodes at the end of the project. And it's a low cost and low carbon footprint. And you'll see from some of the slides after that in terms of environmental and sustainability, it really does tick a lot of boxes. The disadvantages that they thought of was that it's non-standard construction. Yes, it is. But that's also an advantage we see, as we are able to modify the network depending on the ground conditions at the time. So yeah, some disadvantages will also be advantages, obviously. Yeah. Additional soil testing may be required. In this case, it wasn't really. It's advisable to undertake a series of pull-out tests. Yes, we did that. The design life is difficult to understand at this stage. Yes, probably it was. We normally design to 60 years or so. And the sub-horizontal drainage paths may be difficult when the slope is shallow. Yes, correct. What we would do there, and this is normally at the base of the slope, if the cathode's been put in below the horizontal, then we would use, and we used, small 12-volt pumps to dewater those cathodes. So another few things from the original report in terms of option 5, and you can see the 5 options on the top left there. This is a table that included really, in terms of cut and fill and amount of material transport that would be required for each option. and obviously excavation and slope regrade and things like that. You're moving material around. You will be taking material away. You may be moving gravels or other material in, and you're using big bits of kit to move fill around. Now, with option 5, it doesn't come to play with EKG. We don't require it. There's not even a footprint there. It's not something we consider. So again, in terms of carbon footprint and sustainability and what have you, those sort of metrics looks quite a sort of interesting option. We also did while we were doing this is that we looked at measurement while drilling, because we didn't have the opportunity to take this material and do some specific EKG tests with the soils. So we thought we'd take advantage of all the anodes and the cathodes we're placing into this slope. Let's get some data out of it effectively. These are dynamic probes, and let's use it. Let's be smart about this, and let's use it the best we can. Now, this obviously reduces design time, it reduces cost, because we're not doing a separate drilling program. So there's carbon emissions and what have you. And it's just a smart way of working. And we then took this data and then compared it to the GI data that we had, and CPT data and the borehole logs, etc., etc. So just developing our understanding of the area. The installation itself, if we look at the comparison between design and as built, yeah, it's pretty much spot on in terms of cathodes and anodes. You can see from this table, there's not much difference. There's a bit of difference in some angles and what have you, but you know, not a lot. So I think it was 0.2% or something variation. Some of that is around that, you know, we didn't know in absolute detail what this site was about. So sometimes we would move an anode or a cathode because there was a tree at that point. So we'd shift it to the right half a meter or whatever it was required to get that installation in place. So generally speaking, the design and the as-built were as the same. In terms of the implementation, it was activated on the 4th of July last year and operated for 64.5 days. 6 days was lost due to an AC generator failure and shut down. That took a bit of a time to replace it. And then from that point onwards, we collected a whole host of data, power data, water discharge, pH, current, pore pressures. We had some instrumentation on the site, inclinometers. We also measured on track laterally and vertically, because that was seen as part of the risk profile. And then also electrical and electromagnetic monitoring trackside as well. We wanted to ensure that the client was happy that by placing a current on the side, it wasn't going to interfere with their signal systems. Yeah, so once the project was completed, we converted the 183 anodes were converted into soil nails as part of the cementation process that's happening throughout the project. We also grouted some of those cathodes that were not draining, or not self-draining, I should say. We estimated that between 40 and 50% of the cathodes still remained open and are effectively long-term drainage systems. We'll look a bit about some of the data. So this is current data, and if each individual of these blocks, yeah, these colours here, are registered as a sort of average over a fortnight, yeah. So you can see, and this is current dropping. So these are the columns. The columns are on the cathodes, yeah. So these are vertical columns along the grid, covering 75 meters. And you can see that each one is showing a standard pattern whereby the currents are reducing over a period of time. This is indicating that soil moisture is also reducing as well. And this profile also gives us a profile across the slope itself as well. So there's changes in geology across this slope as well, which results in this sort of work. Our consumption across the project. So we looked at a total surface area, soil volume of 5,240 cube of soil was treated across these zones. These electrical expressions, so megajoules per cube, that's a measurement of what drives the osmotic flow of soil moisture from anode to cathode. That's driving dewatering, yeah. The MC squared average, it relates to the development of the soil bond around the anode to the surrounding soil. The averages that come across here are fairly similar to other projects we've been involved in, and we're not far away from what our expectations were. Over a week, we ramped up to 80 volts across the grid, and that remained pretty constant as we went through the project. Dewatering, this is cumulative groundwater, so we took out 30,500 litres of water, which works out to 2.6 litres per cube. There's a bit of a gap here. That was where the AC generator went kaput, and we had a 6-day stand down, but you can see a generally good cumulative curve occurring, but sort of flattening out towards the end as a lot of this soil moisture came out of the slope. Here's a section of what we were working on prior to starting. This was a predicted consolidation, and you can see that you've got the ballast overlaying the clay, and this is one of the reasons why this area is considered some risk. Now, obviously, the electro-osmotic consolidation is occurring within the clay-bound area, and passive drainage would occur within permeable ballast type material. And in this section, you can see these orange lines here are the anodes as they're passing through, yeah. This gave a general consolidation across the area of 12 mil. So just taking a step back from the project, we had a look at it and thought, well, you know, what we're learning from this. So pull-out tests were greater than design requirements, which was pleasing on the anodes. The measured bond was commensurate with the constructed data and the predictions and the treatment time required. Energy consumption was compatible with expectations and other sites. Inclinometers indicate a stable slope and a cessation of movement, which is a tick. Obviously, there's further monitoring going on. Active cathode discharge and data, we look to improve that. Passive cathode drainage was effective. Post-treatment, none has been undertaken as yet, and I'm not quite sure what the plans are to date. We're still talking with Network Rail. There was a calcification in some of the pipework due to carbonaceous material, or sorry, calcite material in the soils. We just dealt that with a bit of a weak acid, and we changed the pump filters to a different grade to handle it. We look at the benefits, and you can see from the right-hand side here. So those are anode plates, yeah. You can see how we've worked around the vegetation. Nothing's been knocked down, chopped down. It's about dewatering a historically problematic embankment successfully, consolidating and strengthening the soils, placement of soil nail reinforcement, as you can see there, the production, the introduction of a permanent drainage system through those drain cathodes. And this led to the benefits, obviously, of very light touch in terms of installation. There's no topsoil, no vent removed, there's no vegetation disturbed, really. Extremely low carbon footprint. There's no traffic management was required, and obviously, very importantly, in terms of rail project, no line possessions were required at all. We're also adaptable. The system itself is adaptable to changes in ground conditions and any other obstructions that are on the site. And it's a sort of technique and a methodology that's not affected by poor weather conditions. So as we come to the end of this, it's probably just as well to sort of, let's also open up a little bit. EKG, we have lots of other applications of this as well, not just in terms of slope stability. We are engaged with a global mining company to look at the dewatering of mine tailings. We also use EKG on like a mobile method in terms of dewatering within the tank environment, dewatering difficult slurries and sludges that are not really suitable for conventional hydraulic dewatering, and dewatering them much quicker so they can be disposed of in an effective manner. So pretty much on time. I hope you found that interesting, and we would appreciate your questions and try to answer them the best we can. I'd also like to give our acknowledgements to BAM Nuttall, who were the engineers on site on this particular site, and we worked with them in an effective manner. And yeah, we can't work without engineers on site being part of the program, really. So I'll share my screen. Hopefully you can see me after all those words. And here's Matthew on the right hand side. He'll be on my right hand side. Perhaps we've got some questions. Anything come through, Matthew? Has got any interesting things to talk about here?
Thanks, Dave, for that. I've got a couple. I don't know if there's any more that might want to come in, but we can see if you can deal with these ones initially. I don't think you touched too much on the ground investigation. So question here, what ground investigation and testing is needed for design of the electrokinetic system?
Yeah, there was a whole raft of data that came through from various reports in terms of conventional GI test work. But what we tend to do as well, we've got to understand what, from an electrokinetic perspective, are these materials conducive to being affected by electroosmosis, and we would normally do that within our own test environment. We didn't have an opportunity this time to do it, but normally we do.
And then this probably relates to it as well. I think you touched on at the beginning in terms of clay being suitable, but are there any more specifics? Is it really what ground conditions are most suitable in terms of specifics?
Yeah, it's about the fine-grained nature of materials and their reluctance to conform to sort of normal hydraulic dewatering, but it's also about the orientation and the thickness of these materials, and obviously the sort of geomorphology of the slope as well obviously plays a feature on this, you know. But quite obviously as well, I mean, slurries themselves can also be dewatered in this fashion, either in a tank, or we have some bags where slurry material can be put in the bag. In this case, the cathodes are sewn into the bag material. That induces a higher flow, higher moisture rate flow from the central anodes through the bag because of the cathodes. and then ends up dewatering slurries and what have you much quicker than you would normally. Any other questions, Matthew?
One's just popped up. How do costs compare generally to the other remediation options that were considered?
I would get that sort of depends upon scale, I would have thought, because one of the major features of this sort of work is that we're not moving round, putting in tons of material and taking away tons of material. So, yeah, costs are favourable when we've done cost analysis to other options. Obviously, the scale of the installation does have some impact on that.
Another question here. What sort of reduction in groundwater outflow is seen when the current is switched off? Supplementary, what's the cost benefit of EK over just installing closer spaced soil nails and horizontal drains than the anode and cathode?
Yeah, in terms of flow, you'd be hard pressed to sort of see an instantaneous reaction, but certainly I think you saw from that graph where the generator had brought for 6 days, and I think we did see within that 6 days we saw a sort of decrease in drainage from the cathodes.
Yeah, can I just jump in there,
yeah.
Dave? When you switch off the power, the electroosmotic effect stops immediately, so that does stop the flow.
Yes, it does, but I mean, you don't always see that immediately at the cathode, quite obviously.
Yeah.
And what was the second bit of the question?
Second question, what's the cost benefit of EK over just installing closer spaced soil nails and horizontal drains than the anode and cathode?
Yeah, I guess it wouldn't just be about cost benefits analysis, it would be about performance as well. Yeah, look, I mean, if you were going for a soil nailing type arrangement, then it would be, you'd just be putting more costs into it. The real differentiator here in terms of electrokinetic is that you're using very low sort of current ratios to encourage movement from anode to cathode, and therefore doing the dewatering. So you're in danger of comparing a little bit chalk and cheese, yeah?
Is the dewatering a cyclic process, or we carry out dewatering only once for the design life of 60 years?
I don't suppose that the actual work would last 60 years. I don't envisage that an installation would be that time period. We are looking to get in there, do the work, and stabilise that slope as quick as we can.
So it's effectively a permanent strength gain.
That's right.
As you consolidate the soil by dewatering it, and you get a permanent strength gain. Do you have an approximate cost per meter squared, meter cubed for this type of system?
No, because we like to these systems are quite unique, but we can, I'm sure whoever's asked that question, I'm sure we can get some broad cost to you. Off the top of my head, it wouldn't be right to sort of answer that, and I don't know it off the top of my head, to be perfectly honest. But yeah, let's have a look at that, and we'll get back to you in more details. I'm sure we've got your details.
We have been recently pricing up some work for some other trials elsewhere as well. So
yeah, that's right. So we've got a pretty good angle on it.
Into that. Yeah. Hi, did slope inclinometers form part of the GI before your involvement, and were they regularly monitored prior to, during, and following the works?
Yeah, there was a lot of instrumentation put in prior as part of the TGP studies and work that was done by Network Rail. And I guess, yes, those were certainly looked at during the project and are continue to be looked at now, I would suppose. What we would like to see in future, and what we certainly would do in future, is that we would look to put our own, if sensors weren't already being used, we would put our own sensors in place and have those as remote sensors that we could pick up throughout the project, and indeed as the project settles down post-project.
Next question, is there a risk of shock for site operatives while the EKG system is in operation, and what is the required voltage to run the anodes and cathodes?
Yeah, you saw it was 80 volts across that, across the grid. Very low voltages. We make sure that the arrangements are safe. We make sure that the staff that are installing these and maintaining these things are understood where the areas of danger are. It's not a high current or anything like that, and it's quite a passive way of doing things.
I'll add to that as well, Dave. During the works, when the instrumentation was being monitored, the inclinometers, etc., the system was switched off for a couple of hours to allow that kind of person access. And itself, turning the system off doesn't really impact the treatment. It will just extend the program slightly, but it doesn't have a big effect on the effectiveness of the treatment. Next question. Were any remedial works required as a result of any settlement or unforeseen consequences from the dewatering?
No, not that we're aware of, and there wasn't a vast amount of settling. Also, as well, there was rail monitoring, as I'd mentioned, and that was quite minimal in terms of settling of the rail track, and as normal as they tend to operate these things. They've got a program of monitoring these all the time, so we're not aware of any ongoing remedial action due to the project.
Again, I think there was with that ongoing monitoring, there was limits for movement, and on one occasion, movement was starting to approach that limit, but it then settled down, and that wasn't an issue. I think that about covers the questions. I don't know if anyone else has got any more they want to type in. Oh no, sorry, one has come through. Having worked with EK on the M5 Junction 7 many years ago, it's interesting to see how the system is still being used. Thanks. Okay, so a nice comment. Thank you.
Thank you very much, and it's something that we're quite proud of. And I've got to say, in terms of electrokinetic in slope stability and in other applications, we are global leaders on this, and we shouldn't be shy about this. We are global leaders on this type of technology, and it's a patented technology, and it's a good example of British innovation, in my view, as well. So it's something that we should be quite proud of. And thanks for the gentleman or lady that pulled up a previous project, and we look to do more in future.
Thank you, everyone.
Thank you, and please feel free to contact us at any time if you've got any more questions or anything pops into your head. We'll get back to you, and we'll address those if we can. Thank you very much for your time. I appreciate, we appreciate all your attendance, and have a good rest of the day. Thank you very much.